Suddenly, a Dalek walks into my classroom.
So there's this hunter, and he wants to shoot a monkey for some reason.
Welcome back. This time we're going to introduce a little bit of algebra to figure out two new equations from our source equation. We're going to have a look at calculations involving echoes, and we're going to have a look at motion graphs. So first of all, what do I mean by deriving a new equation? Well, we have this equation here which says average speed is distance over time, but built into that there's actually two other sort of equations that kind of come with it for free. And when you get efficient at this in physics, you'll be able to automatically have a look at this equation and figure out what an equation would be for distance or another one for time. But since we're just starting off, I'm going to go through this quite carefully and make sure every single step is there. So for the first one over here, I'm going to try and find a new equation, one that will allow me to calculate the distance something has traveled if I know the speed and if I know the time. The first thing I'm going to do is I'm just going to take a copy, and then I'm going to say I don't really want to have the time on the bottom here. You see, I want to get the distance term by itself, and unfortunately just now distance has been divided by the time, and that's kind of in my way. So what I want to do is something that will cancel out that time, get rid of it, so that distance is left by itself. And here distance is divided by time, and the opposite of divide by time is multiply by time. So what I'd like to do mathematically is multiply this side of the equation by time. There's a bit of a problem though. If I only just do that, well sure it will end up changing this side, but it will mean my equation is no longer true. You see, this equal sign tells me that this thing here is the same as that. And if I change one thing on this side, but I don't change the other side, well then surely if they were equal before, they won't be equal afterwards. It's a bit like if you have the same amount of money in each pocket and then you add some to one pocket but not the other, then obviously you're not going to have the same money in each pocket afterwards. So my one rule that you always have to keep track of is you can do whatever you like, but you must do the same to both sides of the equation. And here I'm going to choose to multiply both sides by time, or t. Once I've done that, I'm going to make another copy, and then I'm going to say that time divided by time is just the same as not doing anything at all. If you imagine it, say the distance was 20 and you were dividing it by 5 seconds, 20 divided by 5 and then multiplied by 5, well that's still just 20. So I'll copy out again, this time without the things that are cancelling out, and we're almost done. I want to rearrange the order a little bit, so I want distance to be on the left, so I'm going to swap the equation around. That's not really changing anything. And then because physicists are a lazy bunch, I'm also going to swap the order of these terms around just to match what's normally done. And finally, I'm going to skip out the multiply sign. It's just because it tends to clutter things up and we prefer to be nice and clean. That's my first new equation done. Distance is equal to your speed multiplied by your time. So if you're going to travel at say 10 miles an hour and you do it for 2 hours, in that time you will travel 20 miles. That's how it works. The time one is slightly more complicated, but it's following the same process. The first few steps are the same, so I won't talk you through them again. But this time, once we get here, what I want to do is I want to get rid of this speed term. You see, I've got time up at the top where it kind of wants to be, but it's still attached to this times speed. So now what I want to do is divide both sides by speed, and that way these two are going to cancel out. So that's shown here, and finally we just write it out without the terms we don't need, and we're done. That's my second rearranged equation. It usually helps to have a few examples to see how these things work in action, and that's what I've got here. And first of all, using ones where we're finding the distance, it might be, say, a car's traveling 40 miles an hour for 3 hours, and we're asked how far did it go. Now I'm sure you could just look at that and figure out the number straight away, but I'm trying to get you into the habit of using the equations to support your working. At the moment, while it's new, it actually makes things slightly harder, but if you develop these skills and these methods, it will help you over and over and over again when you do future work. So a good idea to help you keep track of things for each question is to say, right, here's my sentence. Sometimes it's tricky though, and you want to pull out each piece of information and figure out what symbol that's for. So here, 40 miles per hour, that's my speed, and the symbol for speed is V, so I write that here. My time is 3 hours, and I'm going to write, yep, T equals 3 hours. Then if I'm looking at a list of equations, then I can sort of identify the one I want. And this time, to find distance based on speed and time, this is the one for me. So I write out my equation. You might say, well, why do I bother writing out if the teacher already knows this equation too? Well, you write it to show people that that's the one you are using. You write it to say, I know this thing too, and my calculation is based on this rule I learned in a physics lab. Next, you put the numbers into the right place, and finally, you put them into your calculator and have a little bit of a think about the units. So here, this unit was miles per hour, and we did that in hours as well, so the hours kind of match. So you end up with miles as a result. For the next example, our person is cycling at 12 meters per second for 20 minutes. How far did they travel? Well, you could do all sorts of different units if you wanted here, but I'm going to stick with a standard one and say I want my distance to be in meters, and the problem is my speed units are in meters per second, but my time is in minutes, and those two things don't match. My two time units are different. So I'm going to say 20 minutes is the same as 20 multiplied by 60 seconds, and then my calculator tells me that's 1200 seconds. Once I'm ready to go, I can then write out my equation, put my numbers in, do the calculation, and remember my unit. Up here, the questions seem similar, but it's a little bit different. We're told a car is traveling at 30 miles per hour. That's a speed. We're going over a distance of 150 miles, so distance equals 150 miles, and we're asked how long did it take, how much time. So you have to figure out that we're going to use this equation here, not the other two, and then start from there. As usual, we write the equation, then we put the numbers in, then we write down the thing in the calculator, and finally we remember the units. For the last one here, our cyclist is going at 20 meters per second, and we're told they're on a 5,000 meter race. We're asked to figure out their time. Just like before, the previous one, time is distance over speed, 5,000 over 20, which is 250 seconds. You might decide that you'd rather put this into minutes and seconds, and if you remember that 60 seconds makes a minute, you could fit 4 of them in there, and you could express it this way. But in general, I prefer you to leave it in seconds. It's just the preferred scientific way, and this unit conversion can be a little bit tricky. So that's that lot. A general point that's worth making here is that most people are happy with this middle equation. It makes sense that speed is distance over time because that's what we mean by the word speed. People are also happy to think about and figure out this one. They say, well, yeah, I can picture how much distance I've traveled is the same as speed multiplied by time. And people are less happy with this one here, but they can kind of figure it out if they think about it long enough, usually. But the thing is, in physics, you don't need to be able to picture the equation working. If every equation was obvious if you thought about it, well, it wouldn't really be that important. The nice thing about deriving equations like we did on the previous slide is I don't need to understand why time is distance over speed. I just know for sure that it is. And then I can write down my equation and I follow it like a recipe book. If you've ever baked a cake, no one sits there and reads, all right, crack 3 eggs into the bowl. No one sits and goes, well, why is 3 eggs the correct number? Why isn't it 2.5? Or why do I have to put the eggs in now? No one feels the need to challenge every instruction in the recipe book. And the same should be true for your equations. If you know you have a good equation that tells you what to do, then all you need to do is follow it. Don't worry about why it's true, just follow the instructions and it will get you there. I have a different example for you now involving what I'm calling an echo calculation. This is often introduced as a bit of a problem-solving trick, and it often confuses people to begin with. It's fairly simple once you get the idea. It's just people tend to struggle to concentrate on all the different parts that are going on, and sometimes they lose track. But anyway, the story goes, Alice and Bob here are outside and they want to measure the speed of sound. You see, they don't have the fancy timing box that we talked about last week. So they're going to use a different method, a traditional method. And what you do is you take a pair of wooden blocks and you bang them together. And that makes a very loud noise, travels through the playground, reaches a wall, and then the echo from that signal will come back to you. And when you hear it, you stop the stopwatch, and that tells you what you need to know. You can measure the distance with a trundle wheel or maybe a big tape measure. You can time this sort of journey quite nicely as well. Because you have a big distance, you can measure a reasonable amount of time. So here, for 50 meters, which is quite reasonable to do, you can make a loud enough bang that you have a fighting chance of actually hearing the echo. And if you ask, in this case Alice, to time this, she might be able to time it. It's possible to time almost 1/3 of a second, but it is a bit tricky. By itself though, this method would be a bit rubbish. So there's a second trick. Rather than trying to do it once, what you do is you set up a regular clapping. You see, I said at the top here, people are quite bad at being perfect timers, at getting things just right. So you don't try and time just one thing, you try and time a rhythm, because people are very good at rhythms. If you ever thought about it, if you have a room full of 1,000 people and someone starts clapping, everyone else in that room can make themselves clap at pretty much exactly the same rate, and that's quite a nice neat trick. So Bob isn't going to bang these just once. What he's going to do is he's going to clap and clap and clap, and he will naturally be able to listen to the echo and match up his claps so that the signals are consistent. Once he's clapping at a regular rate that matches it, well, one signal comes out, reflects back, and by the time it reaches Bob, that's when the next signal happens. And this helps him be consistent, and it makes it a lot easier for Alice to time. So once Bob's doing this at a regular rate, it's now more predictable, and Alice can match up the stopwatch a lot easier. But we can go even further, and instead of measuring just one of these claps, we might do it for 20 or maybe even 100. So that way, if Bob makes a bit of a mistake or Alice makes a bit of a mistake, it doesn't matter so much. If you measure 20 of them or 50 of them and you take an average, it doesn't matter if one of them is slightly small and one of them is slightly big, because those effects tend to cancel each other out. In any case, you can carry this out, and I've done this and it works reasonably well. And in this case, we have a distance, and here's where it gets tricky. It's not 50 meters, but it's actually 100 meters. You see, the sound wave is traveling all the way to the wall and then back again. That's what has to happen between each clap. So our distance is double the measured distance, and it's 100 meters. The time, well, if with 20 claps was 5.7 seconds, let's say, then you divide that by 20 to figure out the time for each one. So here that's 0.285. After that, we stick the values into our equation, and we end up with a value that in this case is a bit higher than I would expect, but I just made up the numbers. So this is 351 meters every second. Another application that uses an echo effect is an ultrasound sensor. These little devices are really quite nice for various different things at different levels within physics, and you can see a photograph here with a 2-meter ramp for the higher setup actually. This car here has wheels that just rolls by itself, and it's on a slope, so it'll roll down and actually bounces off the bottom, bouncing, 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 and that's at the higher level. But we also have this car here that moves at a constant rate. It sort of gradually will go the same speed always, no matter what, and you can change the speed by changing the little dial. And last of all, we have this car here, which has a fan on the back, which pushes the air away from it. This means that it gives out a force, and it will actually speed up and speed up and speed up. So this one is nice for showing cases where you want the speed to deliberately change. That's not part of this bit of the course, but you might see that in years to come. In any case, it's the same idea as the previous example. Our sensor sends out a pulse of sound, and it hits off of an object, the echo comes back, and a little microphone in here detects that. By measuring the time for that journey and knowing the speed of sound, it's programmed into the device, we can use that to work out how far away our object is. The other nice thing about this is you don't just do it for one measurement, you do it over and over and over again. You can measure this hundreds of times every second. So you can actually plot a little graph showing where the position of this car is, and even work out things like the speed. or indeed the acceleration. But again, that's not part of this course. So what does that look like in practice? Let's have a look at an example. Here, what we're going to say is that our ultrasound sensor is giving out a pulse that reflects off a cart and it produces an echo. The echo is received 7.0 milliseconds later, and we have to figure out where is the cart. Now, as I said before, the software normally does this for us, but it helps us to understand what's going on. So I want the distance, I know the speed of sound, and I know the time that it's going to take. What I want to do is use the equation distance equals speed times time, but first I'm going to get rid of this milli. Millis are a prefix, and all prefixes mess up the units for our calculations, so before we even write down the equation, we get rid of those. Milli means 1,000th or divide by 1,000, so I can swap milli for that, and then 7 divided by 1,000 is this number here. I can then put things into the equation, and the number works out to be about 2.40 meters. Now you have to be a little bit careful here. This means that the sound signal has traveled 2.4 meters in the time quoted here. That doesn't mean the car is 2.4 meters away, it means it's half of that distance. So in this case, it's 1.2 meters, 1.20. Normally in a test or an exam, you'd get 3 marks for the first part of this calculation, and this last bit would give you an extra one. Part B. Half a second later, the echo time changes, and now it's at 3.5 milliseconds. Where's the cart going to be now? Now hopefully you can spot that if you have half the time, it must be half as far away, and you could figure it out straight away. But we can still write out the working if you like, and it's basically the same sum, so I won't go through it in too much detail. And it does indeed turn out to be 0.60 meters away, or half of the previous value. Our car has moved closer in the half second that it had between these two questions. Now why am I showing you the same sum twice? Well, I want to show it to you because now we can answer a different thing. Question C says, how fast is that car moving? So far we've only been talking about figuring out where it was at a particular time, but now we can go further. If it started off here and then it was there half a second later, well, we know how much distance it's covered and we know how much time it took to do that, so we should be able to work out the speed. Distance number 1, or position number 1 really, was 1.20 meters. Position number 2 was 0.6, and that means it covered this distance here, 0.6 meters, in the half second. Sometimes there's a little triangle that gets used to mean change in distance, but some people don't like shapes in their calculations, so I've skipped that out for now. We have our equation as before, we stick in our values, and we can work out the value of the speed of the car. Notice this is not the speed of sound, that's not the speed we used in these previous calculations, because that was talking about the sound wave moving. Here we said, we know the car was there, we know it was there afterwards, and we work things out from there. The last thing I'll tell you about is a lovely sort of game or competition or contest that we can do with this equipment. If you have an ultrasound sensor, you can download an app called matchgraph. And what that is basically a chance for pupils to get a bit of practice gaining experience using position time graphs or speed time graphs. And it's quite a nice way to basically introduce it. I don't have video clips of this, but I'll have to just tell you about it. The idea is you get given a graph of here position versus time, and what you need to do is reproduce that motion by moving yourself towards and away from that sensor. And the clever bit is if you really pay attention to it, you can figure out what you need to do, and that gives you a big advantage. So it's a great way to encourage pupils to actually pay close attention to the graph, because it's much easier to get a good score if you really do that. So here what it says is, well, you get 3 seconds to get into position, it counts you down, and then you've got to copy. And to begin with, you should be 0.2 meters away, or 20 centimeters away from the sensor. So you have to get in position. And then it tells you that for the first 3 seconds, your position should stay the same. You should stay put. But after that, you have to start moving. And the distance you're at, or the position, is going to get bigger and bigger and bigger, which means you have to move further away. And over the next little time, this 4 seconds here, we're going to move all the way out to 1.8 meters. So that's 160 centimeters you've got to move your body in 4 seconds. It's not too fast, it's doable, but you can't hang about. Afterwards, we're going to stop at 1.8 meters away and stay there for 3 seconds. Now my score here isn't the best, but it's okay. Most people could do a bit better with that if they have a few tries. But as I say, it's nice to work out your exact positions, and to give yourself a bit of a hint, if you were doing this, you could try and work out how fast you're going to have to move in this zone here when you're moving. And you could say, well, my change in distance or change in position is 1.6 meters, and I'm going to have 4 seconds to do that. So my speed is going to be 0.4 meters a second, or 40 centimeters every second. That's a sort of quick movement. As I say, you can't hang about. You can see with my score when I did this here, I was actually too slow. I fell behind a little bit. My personal sort of best score, if you like, if you want to get really competitive, and why wouldn't you, is this sort of challenge problem here. In this case, it's not just a one-off movement, but you have to sort of sway back and forth, and it's really quite tricky to do this one. I've tried this with hundreds of pupils, and none of them have quite come close to this. So this is my current challenge that I leave out for anyone who fancies it. But you can also read into the graph a little bit more. You can see that the minimum position is 60 centimeters away, and the maximum is about 1.4. So I'll put that up here on the graph. Finally, you can also see the whole thing repeats. This is one sort of motion, then it repeats, then it repeats. So there's sort of 3 whole repeats of the same thing. That gives you a clue quite nicely what you're going to have to do. But also, you've only got 3 seconds to do each repeat, which means when you start 1.4 meters away, you've got 1.5 seconds to get all the way into 0.6 away, and then 1.5 seconds to get back. So that's really quite a tricky thing to do. Again, you might work out the average speed if you like. So speed is distance over time, and the change in position here is 0.8 meters. The time we have to do this is 1.5 seconds. So you're going to have to move at about 50 centimeters every second. So again, quite fast. The other thing you can maybe tell is that it's not a zigzag. This is one thing that sometimes people confuse. They just don't quite notice the detail. It's actually a little curve, and you'll recognize it later as a cosine curve. It's quite steep in the middle, and then it sort of rounds off, which means you have to do that with your motion. You go really quick, and then you slow down and brake, and then turn around gradually. That's part of what gets a really good score in this middle zone here. The reason I've included this for you, even though you don't have the equipment, is just to give you an indication of how much information we can get from looking at a graph of something's motion. This is why we like these sensors, and we routinely use them for our senior classes. In terms of the theory of graphs, we can also look at speed time graphs. These are slightly different. Rather than plotting where the car is, you plot how fast it's moving. And this is the last thing I'll tell you about. This first set of graphs are very boring. What it says is we have the speed here of a thing, and that's time, so that's how it changes over time. But all 3 of our plots here, all 3 of our cars, are not really changing. They're chugging along at the same speed the whole time. Car C is quite slow because it's at the bottom. It has a speed of, I don't know, let's say 2 meters a second. Car B has a speed that's higher. That's maybe up at 3 meters a second. And then car A would be, I don't know, 4.2 or something. It's going a fair bit faster. But all of them have the same type of speed. They're all moving at a constant rate. None of them are speeding up. None of them are slowing down. They will never overtake each other, that sort of thing. In this second graph, we have plots that show cars that are speeding up. To begin with, both of them start at speed 0, and car B will get faster and faster and faster as time goes on. The speed value is getting bigger. But car A is going to do the same, get faster and faster and faster, but it's going to gain speed much faster than car B. We would say that car A has the higher rate of acceleration. Sometimes people might think of this when they talk about cars, and the words are usually quite bad. People might say they've got a really fast car, but it doesn't make much sense. Every car is limited by the speed limit, assuming you're driving legally or not on a racetrack. So why would someone pay more money for a faster car if they can only ever go 60, 70 miles an hour anyway? Well, when people say they have a fast car, they're not really meaning it has a higher top speed. what they often mean is the rate of acceleration is faster. It can get up to speed quite quickly, and that's actually quite handy sometimes. If you have to overtake other cars, you don't want to have to spend too much time on the opposite side of the road because it can be a bit dangerous. It takes a more powerful engine to do that, that's why it's more expensive. The other type of speed I'm showing you here is where the speed is slowing down. Some people would say that's a deceleration, but it's better to call it a negative acceleration. And that's basically what happens when you're braking. Both of them here start with a high speed, that's whatever number this would be, and car B is going to brake really fast or really hard. That slows it down really quickly. That's a car with very good brakes, that's very safe, you can stop if you suddenly have to. And car A, well, the brakes aren't quite as good. Or maybe it's a heavier car, maybe it's a big lorry or something. It doesn't matter how good your brakes are, if you're a very, very big lorry, it's going to take you more time to slow down. And there you go. This is one of the reasons why drivers have to be really careful. If it takes a good few seconds for you to stop your car and you're traveling very quickly, even if you hit the brakes as soon as you see something run out, well, it might not matter. You have to sort of plan ahead. It's also a good idea why people shouldn't walk in front of cars and buses. But oh well. The final thing I'll share with you is a little hint for your homework. There are various questions here. Most of them involve these equations as they are. Don't worry about trying to rearrange them, just have them in front of you and pick the one that you think you need. This question here goes into a little bit more detail interpreting graphs, but I think you'll manage that just fine. As I say, just copy out the table and then have a think about the word constant, what that really means. Last of all, it's not related to this stuff, it goes back to one of these equations, but you have to use data from the graph. That can be a bit tricky. Thank you very much for listening. See you next time.